All right, am I audible? And is my screen visible? All right. Okay. So I'll spend a minute recapping what we were trying to do yesterday. So we are trying to find this equation. Uh, on the left-hand side, we have rate at which the amount of entity that is residing in this control volume is changing. Okay, entity could be mass, momentum, or energy. So that is the left hand side, or that the left hand side is the mathematical expression of that statement, whereas right hand side should include the effects of the reasons, or it should include the mathematical expressions of the physical reasons why this amount will change uh, with time, the amount of entity contained in the control volume. So we are segregating all possible reasons under two headings. Reason one is, I have written an extra statement here. The slide is from yesterday, but I have added a statement to make it more clear. Reason one is the net rate at which amount of entity in the control volume increases. When you come back here, due to the flux of fluid across the walls of the CV, 6 walls of the CV. And reason two is everything other than flux. So this statement describes reason two. We go back to what I have written here. The net rate at which amount of entity in the control volume increases due to all other reasons. And we will get to the mathematical form of reason two later, but I started with reason one. So we want to have mathematical expressions for reason one. And since there are 6 surfaces and flux of fluid can happen across all these surfaces, reason one should be the sum total of the individual contributions that will come from the 6 surfaces. So these numbers, indices uh, appearing with C, they correspond to the surface numbers that I show here on this figure. Uh, so C1 is contribution from surface 1. So if I put it in words, it is amount of entity coming into the control volume per unit time due to the flux of fluid through surface S1. So this one corresponds to C1. I wrote this expression here. I I hope that you have read it, I mean paid attention to it, and it appears reasonable to you. I have taken E1 here and there is a minus sign. I realize that some of you may look at it in a different way. You may not want to put a negative sign here. Instead, you may put a minus E1 here. So you may want to dot V with minus E1. That is also fine as long as you get an expression which is consistent with mine overall, sign wise and dot product. It should be okay. So what is important here is to keep in mind that I am asking this question coming into the control volume. So you have to take care of the sign properly. And when you go to the opposite surface, C2, surface S2, uh, which is still perpendicular to E1, but it has outward normal in the other direction, then the question remains the same, amount of entity coming into the control volume through S2 per unit time due to the flow field, and that will again dot with E1, but there will be no negative sign here. Okay, so mind you, I am asking, the overall question is net rate at which amount of entity in the control volume increases. This is what I am interested in, increases, and that's why I am making these statements coming into the control volume, and here also coming into the control volume. All right, so that is one important thing while writing expressions for C1 and C2 minus. You have to pay attention to what unit vector you are using and what sign you are putting. And the other important thing is to note that the other important thing to note is the argument of v vector and phi vector should take into account what surface is under consideration. So for C1, the surface S1 is displaced from center along even axis by delta x1 by 2, and that's why this delta x1 2 appears in the arguments of both v and phi. So that is the other thing you need to pay attention to. And for C2, since we are talking about surface S2, which is displaced by minus delta x1 by 2 in un direction from the center of the control volume, that's why we should have x1 minus delta x1 by 2 in the arguments of both v and phi. Okay, and then I said that this dot is v dot e1 will be v1 component. So now we have completely brought Cartesian components. We have gotten rid of dot product. Then I said we have to use Taylor series expansion up to first order to express v1 and psi on the two surfaces in terms of the values of the corresponding quantities at the center of the control volume, and that will require also derivatives. So let's take these expressions from Taylor series approximation and put it in C1 and C2 combined. So I'm treating C1 and C2 together now. So this is the new slide. This is the first slide for today's class. C1 plus C2 will be what I have written here. Okay, so what I have done, I have actually skipped a step. So I take these V1 and psi, and I go here and I actually take this product, and that's what I have written here. So I am writing it terms after doing the multiplication of the two factors V1 and psi for both C1 and C2. Okay. So for C1 we get 4 terms, right? We will get 4 terms from here, 2 terms coming from V1 because Taylor series gives us 2 terms, and psi will also have 2 terms according to Taylor series approximation. So product will have, thus the product has 4 terms, what I'm showing here. Okay. And you see that C1 has a term involving delta x1, delta x2. I mean, it has a term of order 2 also. Now, when you do consider these two things together, fortunately, many terms cancel out. So V1 phi will cancel out, and even this term with delta x1 square and delta x1 square cancels out. And what you are left with is this term, what I'm showing with cursor, this, and then the second and the third term from the purple box. And you all add all of them, and this is what you get, minus v1 del phi del x1 del v1 del x1 phi, and then delta x1 delta x2 delta x3. Now this you can immediately identify this as a product rule of differentiation. You can put it in a more compact manner, which is minus del x1 v1 psi delta x1 delta x2 delta x3. So as I was hinting yesterday that C1 and C2 when taken together will appear as a very simple expression. I mean, algebraically simple. It will not have many terms, and that's what has happened. You see, this is what we get. Just to remind you, C1 and C2 will have unit as entity per second, right? Because that's what we are seeking, amount of entity that is coming into the control volume through surfaces 1 and 2 per second. So it should be entity per second. You can check the units. Actually, I checked it here. So I'll come to that later in a little while. So just to remind you again, C1 plus C2 is what it means by statement. I just said, I have written it here also. Unit of C1, C2 will be, as I'm trying to show, it should be entity per second. So del x1 is 1 by meter. V1 is meter per second. Entity is entity per meter cube. You remember phi I defined as entity per unit volume. So entity per meter cube, and delta x1, delta x2, delta x3 are, they give us volume. So indeed, when things cancel out, you will get entity per second. So what I'm trying to show that not only, so I expected it to be entity per second based on the language, the words that I put here, and the expression that we are getting in mathematical expression that is also having the same units as it must be. So it is kind of a check to ensure that the mathematical expression is at least dimensionally consistent with what we were looking for. Okay. All right. So C1 and C1 plus C2 we have taken care of. Uh, I have C3, C4, C5, and 6 left. And next I will consider C3 and C4 in pair, as a pair, because we saw that as a pair when you take the expressions become very simple. So I am going to write I'm going to make an attempt to write C3 plus C4, recognizing the pattern that is revealed or that is exhibited in the expression of C1 plus C2. Um, Again, if you wish, you can derive C3 plus C4 from first principles. First principle, I mean this way. You can write C3 explicitly, C4 explicitly, and then do Taylor series expansion, then simplify everything and get to the final answer of C3 and C4, or you can just recognize the pattern. For this class, I am going to just recognize the pattern and try to write it. So how do I recognize a pattern, if any pattern is present there? So this was C1 plus C2 with surface normals along E1. So both surfaces S1 and S2 from where we get, for which we got C1 and C2, they had surface normal along 1. And what is the significance of surface normal along E1 axis, I mean, or one direction? So what is special about this expression that relates it to the fact that it has to do with E1 axis? See the indices for V, and index for V and index for X. Both are having 1, 1. And this one is like neutral to the direction. It has indices for all the 3 directions. So certainly we don't have to worry about this. Anyway, this represents the full volume of the control volume. So indeed, one is showing that it has to do with those surfaces had to do something with E1. So now C3 plus C4, if I am asking for. So C3 plus C4 are related to surfaces uh, 3 and 4, and they are indeed surfaces which are perpendicular to 2 axes. So I will look at this, replace these ones by 2, and this should be the expression: minus del x2 v2 psi del x1 del x2 delta x1 delta x2 delta x3. And then C5 and C6, they are from surfaces which are normal to E3, so they must add up to give what I have written here: minus del x3 v3 pi delta x1 delta x2 delta x3. Okay, so now we have this all this C1 to C6, And now I'm going to go back to the starred equation, slide number 3. If you go back, I have written slide number also, this equation, right? This I'm calling a starred equation. So reason 1, I have found the mathematical expressions now. So I am going to replace reason 1 here by C1, sum of C1 to C6, and this is what you get. Left hand side you have del partial of phi with t, and right hand side this whole bunch of terms represents C1 to C6 summation, plus reason 2, for which I have not found mathematical expression yet. So I am leaving the words here, leaving that word here as it is. Uh, Now let us divide everything by delta x1, delta x2, delta x3. Okay. If you do that, left hand side will be just a partial of phi with time, and this will be this had delta x1, delta x2, delta x3 sticking originally to it. You divide and you get rid of that, and finally reason 2 will have delta x1, delta x2, delta x3 in the denominator. I have done another small modification here. I have taken this right hand reason 1 by delta x1, delta x2, delta x3 to the left side, and I will make it, I will present this equation in this manner. Okay. Later in next week, we will recognize that there is a very good reason why we should take these bunch of terms on the left hand side, because by bringing them on the left hand side and clubbing those terms together with the partial time derivative term will give us a very good opportunity to attach a physical meaning to the left hand side. So that is the reason we take it to the left hand side. Algebraically, of course, it doesn't make any difference, but this is the way people most of the times present this equation. All right. So our next task is to find reason 2. And as I said in the last class, that to get to a mathematical expression of reason 2, I cannot deal with psi in a general form. I will now have to take 3 different cases, making psi first as mass per unit volume, then momentum per unit volume, and then energy per unit volume. Only then I will be able to identify the mathematical expression of reason 2, because reason 2 is the mathematical expression for reason actually governed by one of those 3 natural laws: conservation of mass, Newton's second law, and first law of thermodynamics. And they have uh, different agencies on the right hand side, or different terms on the right hand side. So I cannot keep this treatment general now onwards. So I will have to take them specifically one by one. Okay. So this is a summary slide. Again, it's written the same equation, and this is what I said. Reason 2 can be determined by the natural law corresponding to the entity under consideration. And just to help you get everything on the slide, I mean, all that information summarized on the slide, I have made this table. If entities, mass, momentum, total energy, what determines expression for reason 2? For mass, it is law of conservation of mass. For momentum, it is Newton's second law, total energy, first law of thermodynamics. So, so this is a cartoon that I'm trying to, I've drawn to draw your attention to the fact that, see, this is what is in the background. We have a frame, observer, flow field, white space. He goes to a location X at time T, and he is inquiring about phi, what is the value of phi. And what I'm trying to tell you is that the answer of that phi should come after we have been able to solve an equation of this sort, what is shown in star. So this can be called, what I have on the left hand side can be called as the governing equation of phi. Of course, it's not complete, but this is how, this is kind of a primitive form of that equation. Now, the other thing I want to highlight is that looking at what you have on the left hand side of the star equation, it should be clear to all of you that it is this governing equation is already a partial differential equation. Okay, a partial differential equation. So it is a differential equation, not an algebraic equation, number one. I hope you understand the difference between an algebraic equation and a differential equation. Algebraic equation is x plus y equals 3. This is algebraic equation, an example of an algebraic equation. Dx dt equals 5. This is an example of an algebraic equation, a differential equation. So, but dx dt equals 5, this is not partial differential equation because you have complete d there. Here we have derivatives involved, that's why it's differential equation, but there are partial derivatives like partial with time and x1, that's why we call it partial differential equation. So these governing equations are already PDEs. Okay, I will use this acronym PDE for partial differential equation. Okay, so now let's try finding reason 2 for the case when the entity is mass. When the entity is mass, we have seen it earlier, phi becomes rho, right? So the equation, whatever we have gotten so far, the star equation, I'm going to replace phi by rho. So left hand side is clear now what it should be, and we are only left with reason 2 by delta x1, delta x2, delta x3. Now we have to find expression for that. So to find the expression for that, reason 2, we ask this question: what are the reasons, what is or are the reasons excluding the flux caused by Vxt, excluding, because that has been taken care of on with these partial derivatives. Excluding the flux reason, what could be other reasons that can cause the amount of mass contained in the control volume to increase or decrease? What could be other reasons for mass to increase or decrease? Okay. And to ascertain this, I will give you a hint how to get to the right answer to this question. To ascertain this, for a moment, imagine that Vxt has been switched off. So imagine there is a control volume submerged in a fluid domain, flow domain. Okay. Imagine that for an instant you switch off V. So what happens? Whatever is there inside the control volume, whatever mass is there inside the control volume, it has stopped flowing out, and no mass is coming inside either. Okay, so you have an amount of mass 5 kg. So for a moment you imagine Vxt has been switched off, and then ask what can now make the mass contained inside the control volume to change. So that is what is reason 2, over and above the flux. So if you imagine in your mind V has been switched off, then according to the natural laws that you are aware of, in this case conservation of mass, that much 10 kg of mass, can it grow on itself by itself, or can it destroy itself? Right. The mass itself, can it grow or can it destroy itself? The answer is no. We know that conservation of mass tells us nothing can change it. There is nothing else that can change it. Classical, and mind you, I'm talking about classical mechanics, no nuclear reactions being considered. Of course, if you consider nuclear reactions, we know that mass disappears and becomes energy. We are not concerned about that kind of situation. It's classical mechanics. So classical mechanics, mass cannot be created or destroyed. Thus, reason 2 should be 0, identically at all times. So once if V has been switched off, The amount of mass that is right now residing in the control volume has no means to increase or decrease. There is no mechanism that nature provides for it to increase or decrease. And thus, if entity is mass for case 1, reason 2 should be 0, which means that you already have an equation. And that equation you can call equation for density, because it is the partial with time, and I mean density is appearing on the left hand side with time derivative and also with other derivatives. So you can call this equation governing equation for density. Okay, so this is the form that you get when you are trying to describe. This is the form of this is the statement of conservation of mass when you are trying to describe a flow field in Eulerian way. Okay, you get a partial differential equation like this. Okay, so we got one equation already. And next week, when we are done with deriving all the PDEs for invoking Newton's second law and in first law of thermodynamics, we will summarize those equations, we will put them together, and at that time I also will try to give you more physical insights into this equation. Some very interesting physical insights we can draw from this equation. But for the time being, let's be satisfied that let's focus only on ensuring that we get an equation. And right now I have an equation in our hand. Okay. Any questions? Please feel free to type. I think I am going sufficiently slow, giving you time to grasp what is there on the slides. If you have questions, feel free to type. I'll keep coming back. All right. So this is one equation. The next is I will take case 2. Case 2 entity will be the entity that I will take is one momentum of fluid. I can take entire momentum vector also. I mean, our equation, what we have so far, the star equation can handle that. But you may not be able to follow. Again, the algebra will become too much. So I am taking one momentum of fluid first. And we will derive the equation, and then with pattern recognition we can get the second and third component also. So that's the strategy I will follow for momentum, because momentum is a vector, it can have 3 potential equations. Okay, so first I take one momentum. One momentum means first component or component of momentum along E1 axis. Now once you decide that the entity is one first component of momentum, I hope you are comfortable with me writing phi as rho times v1. And again, everything is at x comma t. I am not writing because it's very repetitive, and also I do not have much space here, so many things I have to write. So that I am not writing, but keep in mind that this is phi and rho and v1, they are all at x comma t. Okay, so with this phi, again I go to the star equation. So left hand side becomes I will just replace phi by rho v1. Okay, see, even with one component it has started becoming complicated now. So for partial with time I have two factors rho v1, and for partial derivative with spatial coordinate I have three factors already. So that this original v1 is coming from the flux physics. I mean, this v1 is the carrier vector, carrier component for causing the flux, which was always there in the star equation. And this phi is now being replaced by rho v1. It brings two factors everywhere. Okay. And also pay attention to this. Since phi is rho v1, there is rho v1 in all the three partial derivatives, but the index of the partial derivative goes with the transporter velocity component, which was here also. So 1, 1, 2, 2, and 3, 3 were here. 1, 1, 2, 2, 3, 3 are here, and then rho v1 comes. So these things you must start training yourself to be careful about, because we will be dealing with these equations almost for the entire course, and you should be aware of what indices are being put where. I'm not asking you to memorize things, but I mean, even looking at the equations, you should be able to make sense why I am putting rho v1 and v2 times rho v1, v3 times rho v1. That kind of awareness and understanding I encourage you to develop. No need to memorize anything. I will not ask you to write this equation in any exam or quiz by any means. I'm not going to test your memory. I'll try my best not to ask any question based on your memory, but some other questions at some time, I mean, I can't rule out this possibility that no memory will be required, no memorize. I mean, you do have to remember a few things, but certainly not this equation. Now, the reason two for one momentum, uh, again, I make it more explicit. Reasons that can cause change in one momentum associated with the chunk of fluid mass currently occupying the control volume, excluding the changes caused by flux of fluid. So that is there. That has whatever is in green, it has been taken care of by reason one. So excluding the flux, what are the reasons that can cause change in one momentum that is associated with that chunk of fluid currently residing in the control volume? So I will tell you to judge or to find out what can cause that change. Again, do the same thing what I said here. For a moment, imagine that V has been switched off. Okay, so no flux happening. Now what you have, close your eyes and think about it. What you have a chunk of mass residing inside the control volume. Okay, it has some momentum, one momentum right now, 10 units of one momentum. What can cause it that 10 units of one momentum to change? And as I hope that you will realize that the reason why momentum, one momentum for that matter, any component of the momentum of a chunk of mass can change, the reason why it can change is actually forces, right? That's what Newton's second law tells us. So we invoke Newton's second law, and assuming that the reference frame in this context is inertial, which I'm taking now, from now onwards, the reference frame of the frame of observation is inertial. So reason two should be one component of the net external force acting on the chunk of mass currently occupying the control volume. That should be reason two. That should be reason two. So the amount of one momentum that can change in the control volume, it can change because some one momentum pours in because of flux, or some one momentum goes out because of flux, that we have already taken into account from the left hand side. Over and above the flux, as I said, you close your eyes and imagine V has been cut off, V has been switched off. The only reason why one momentum can change over and above flux is if there are external forces acting on that chunk of mass. All right. So it means that now to get reason two, what you will have to do is to draw the free body diagram of all the external forces that are acting on that chunk of mass that is right now residing in the control volume. Right now residing in the control volume. Okay. Note that I think it's a good realization to make that that chunk of mass can be called a fluid element. Right now, the chunk of mass that is living in the control volume can be called a fluid element. So effectively, I'm saying to get reason to, you draw the free body diagram of Fe that is there. It's coinciding or occupying that control volume. Okay. The only external forces. I mean, there are fluid particles inside the fluid element, but doesn't matter what those fluid particles, the forces they put on each other. That we don't care about. What we care about is the forces that are acting from outside on the fluid particles of that fluid element or in other words, the forces, external forces that are acting on that fluid element itself. Okay, so that's what we will do. We will try to draw the FBD of that Fe and identify the external forces acting on it. Okay, and once we have gotten those forces, we can bring back, put those forces as reason 2, and we should be able to get our next equation. Now, before we draw the free body diagram, before we finally draw the free body diagram, let's recognize that there are two types of forces that can act on a fluid element. Okay, or rather, I should say that of all the external forces that can possibly act on my fluid element, I'm going to segregate or categorize those forces under two headings. Okay, one is the one is a grouping of so-called body forces, and the other is other grouping we call surface forces. Okay, one is body forces, the other is surface forces. How do I define body forces and surface forces? Okay, so body forces acting on an Fe are those forces that act on each and every fluid particle of the fluid element. Each and every particle, so basically I'm saying whether a fluid particle belonging to this fluid element, whether it lies on the surface of the fluid element or within the body, I mean within the fluid element, doesn't matter. Those forces act on each and every fluid particle anyway. For example, gravitational force is a very good example and the most commonly encountered body force for fluid motion. You will agree with me that that force is acting on every fluid particle of this fluid element, irrespective of the fact whether the fluid particle is right now on one of the surfaces S1 to S6, or it is within, well within the inside the control volume or that fluid element, doesn't matter. So that's what is body force. And surface forces are those forces, as the name suggests, that they act only on the fluid particles which are lying on the surface of the fluid element. So fluid particles that are on the or on the outer surface of the fluid element, the forces that only those fluid particles experience, we call them surface forces. And we will see what those surface forces will look like in a little while. So let's first see how to express body forces, and then we will come to surface forces. As I said, gravitational force is an example of a body force. This system of body forces acting on the FPs of all FPs of Fe can be represented as a single force vector and a moment due to a couple. Okay, equivalent force system. So all the body forces, even though they are individually acting on every fluid particle, we can represent that entire force system comprising of forces acting on individual fluid particle as one single force and one moment due to a couple acting at the center of mass of the fluid element. So this idea is exactly the same what you have seen in APL 100, that you have a body and then there are many forces, some distributed forces, some point forces, many forces acting on that, and then you say what? I am going to replace this force system comprising of numerous forces by one single force acting, one single force and a moment due to a couple, and I will put those at the center of mass of the body. Right, that's the idea I'm trying to convey. So that's how I will represent body forces on the fluid element. I will put one force, and I would like to put one single force and one moment due to couple at the center of mass of the fluid element. But then for most engineering fluids, fluid flows of engineering interest, you do not experience a force system which requires actually a couple. Again, gravitation is a very good example. Since it is a parallel force system, all fluid particles are experiencing gravitational force, but the vector, the force vector for all of them is pointed in one direction. So this is an example of a parallel force system. And again, from APL 100, you would know that for a parallel force system, the equivalent force system does not require any moment due to a couple. All it requires is putting a single force at this at the center of mass of the body. Okay, so what I'm saying is, in fluid mechanics, most of the times we deal with forces, force systems, body force systems, which are like this. And thus, for such applications, the entire body force system can be represented by a single force vector only, and the magnitude of this single force is the magnitude of the sum of forces acting on individual FPs of the FE. Okay, so gravitational force I will replace as one single force acting at the center of FE with magnitude mg, where m will be the total mass of the fluid element. That's what I have tried to show here. I've already said enough about it. This is eventually what a body force like gravitational force will look like on this fluid element, which is coinciding with the control volume. One single force, and the magnitude will be g times the mass inside the control volume, or the mass of the fluid element that is there coinciding, and that mass must be this rho times volume. Okay, now let's come to surface forces. So body forces is already something close to what you are familiar with. Surface forces may be somewhat new. I mean, their formulation may be somewhat new. So who exerts surface forces? My first question is, who exerts surface forces? Those FPs which are lying next to the FPs of our FE, they exert surface forces on our FE, right? Neighboring fluid particles which do not belong to this fluid element, they are capable of putting forces on our fluid element. So surface forces are coming from neighborhood of the same fluid but of a different fluid element. Surface forces are expressed using a second order tensor called stress. Stress is a second order tensor, so for the time being we leave the governing equations aside and first learn more about the stress tensor itself. Okay, so I'm postponing drawing the free body diagram for a little while, maybe for a lecture, one lecture, because we need to get familiar with this new quantity called stress, with which we will be able to quantify the surface forces acting on our fluid element. Now, in Eulerian description, stress tensor, which I'm denoting by sigma under bar, can also be expressed as a variable. So mind you, this is a variable. It is dependent on time and space like pressure or temperature or other primary variables we are familiar with so far. Since it depends on x and t, stress is defined at a point and at a given instant. So you can talk about stress, that stress at this point is this much at this instant. All right, so it can change from one location and from one time to another. Cartesian coordinate system sigma can be expressed as what I have shown here, following what we learned in the first two lectures. Right, sigma ij, eij, and I'm using this frame embedded Cartesian coordinate system. Sigma ij can be called the ijth component of the sigma tensor itself. Now let's try to understand physically what it means, and only when we understand physically what it means we will be able to use the appropriate terms of sigma tensor. So it has 9 components, appropriate terms of components of the sigma tensor to get our free body diagram right. So what does the sigma 11 or sigma 12 or sigma 13 mean? What is the significance of these indices? So suppose there is a flow field. Suppose there is a flow field given. Okay, again the white space of this slide. And imagine the flow field being cut into two parts by a plane which has unit normal along E1 and contains the point x1, x2, x3. So I want to know the physical meaning of sigma 11, x1, x2, x3, comma t. So for that, what I'm doing, I'm going to x1, x2, x3 and letting an imaginary plane cut the entire fluid or the entire body of fluid into two parts, left part of fluid mass and right part of fluid mass. And the surface with which I have cut, the imaginary surface with which I have cut the fluid mass into two parts, I have used a surface which has normal as E1. I think this should be E1 rather than En. Okay, so in this case, I have, for this special case, I have used a plane which is has unit normal as E1, and that plane contains x1, x2, x3, right? Now consider the left part of your system. So after making this imaginary cut, throw away this right hand part completely and focus only on the left hand part. So now consider this as your system. Okay, consider the left part as your system. Now imagine a small area delta A on the left face of on the left face of the no, sorry, on the cut face, whatever the new surface has been created by cutting, on the cut face of the left part centered at x1, x2, x3. So I go to x1, x2, x3 and I imagine a small area and I call it delta A1, delta A, delta A. The outward unit normal to this area is E1, of course, because I have taken the left part and I'm focusing on the newly created surface of the left part. So you consider an area delta A, the outward normal will be along E1, right? Now, on this surface, identify the force vector delta F that is being exerted on this area belonging to the left part. So who is exerting this delta F force? Of course, the part that has been cut and removed. So delta F is the force that the right part of the fluid was exerting on the left part through this area delta A. Okay, so delta A is experiencing delta F force because of the right part. Let's express this delta F force, which is vector, as delta F1 E1, delta F2 E2, delta F3 E3, three components, Cartesian coordinate system, same Cartesian coordinate system. Then sigma 1 is defined as I have written here. So you take this delta F1 force component, divide by delta A, the area, which is having unit normal E1. Take the limiting value. That is what is the definition of sigma 1. And sigma 12 is defined like this, what I have shown. So area remains the same. I mean, you are still talking about the same area which I have identified with unit normal along 1. So this 1 is actually telling me, the first index of 1 is telling me orientation of plane used to cut fluid mass into two parts, whereas the second component is telling me the component of the force what you are focusing on. And similarly, sigma 13 will mean limiting value of delta F3 by delta A going to 0. In this way, you can attach similar physical meanings to sigma 21, 22, 23, and other components as well. The first index tells me, as I'm repeating, orientation of planes to cut, make that imaginary cut on the fluid mass to make two parts of it. Orientation of the plane, okay. And this 2 component will mean the component of the force. All right. So this is how we define sigma. Now there is some sign convention that we follow for sigma components. Sign convention for sigma ij component. Sign of sigma ij is positive. Sign of sigma I. So mind you, the sign of sigma is not governed by sign of delta F alone. That's the point I'm trying to make. Sign of sigma ij component is not governed by sign of delta F alone. Area also plays a role. How it plays a role? Sign of sigma ij is positive if outward unit normal is along EI direction. And delta Fj is also along positive EJ direction. Okay, that's one rule. Also, sign of sigma ij is positive if outward unit normal is along minus EI direction and delta Fj is along negative EIJ direction. Okay, so these two combinations will keep the sign of sigma ij positive. If both the outward normal and the force vectors are in pointing towards positive EI direction and EJ direction, then it is positive, and both of them are negative. Even in that case, it becomes it keeps the sigma ij keeps its positive sign. I have some examples here. Okay, otherwise sigma ij will take negative sign. If these two rules are not applicable, then in all other cases sigma ij will have negative sign. So I have some examples here. I'll just take 30 seconds and then stop. Uh, so this is the surface I'm considering. I'm considering the left part. So what is the outward normal? It is along plus E1. And if the force, this force, which is right now in two direction, you have to refer to this coordinate system. If you have a force of 5 Newton acting on this area in along positive E2 direction, so what do I have? I have the unit normal of area outward, unit normal of area along plus E1 axis. The force is along plus E2 axis, and that's why sigma 1, 2 will be 5 Newton per meter square. And here I'm assuming that the area is unity. That's why 5 Newton will become 5 Newton will still be 5 Newton per meter square. So this will be the case with plus 5. Now consider this situation in which you have focused on the right part of the fluid. And if you focus on the right part of the fluid, then the outward unit normal is actually along minus E1, because you are referring to the same coordinate system. That doesn't change. And if the force is along two direction, if the force that we are focusing on, the component of the force that we are focusing on is in minus E2 direction. So component of force is in minus E2 direction, area is minus E1 direction, still you keep the sign of sigma 1, 2 as positive. That's what I was trying to say here on the left hand side of the slide. Take another example. I go back to the left part of the fluid, and again my outward normal becomes E1. Again, outward normal means going from the part of the fluid, that going away from the part of the fluid that you are considering. So here I'm considering the left part of the fluid. That's why the outward normal, so-called outward normal, is pointing away from the left part, right? I hope you have gotten that idea clear. So outward normal is plus E1, and if the force component turns out to be along minus E2 direction, then sigma 1, 2 must have minus sign. So that would be fine, minus 5 Newton per meter square. All right, so this is the sign convention we will follow. I stop here, and if you have any questions, please let me know. So now what we are going to do, just to give you a hint where we are going towards, what we are going towards with this sigma, I am going to write or draw the free body diagram of that fluid element, which is right now in this control volume. I'm going to draw the free body diagram. Of course, I will put body forces as they are, but surface forces I'm going to write as components of sigma. All surface forces will be expressed on the free body diagram as components of sigma. That's why we have defined this new quantity, sigma. Stress. Is surface tension an example of surface force? Yes, it is. Yes, because that force is, if I go by my definition of surface forces, forces that are exerted by the neighboring fluid particles on the fluid particles of my fluid element, those fluid particles which are on the surface. By that definition, yes, surface tension force uh, will be counted within using this symbol sigma. Viscous force is body force or surface force. So you tell me, Jitendra, you can unmute your mic. Very good question you have asked. Very, very, very relevant for us. What is your guess? Viscous force should be a body force or surface force. You guess and then I will confirm. You can speak up.
So I think it should be, yeah,
Hmm.
hello.
Yes.
It should
No, it
be,
should be. I didn't get
sorry, sir.
your voice. Are you saying is it a it's a surface force?
No, sir, it should be body force.
Oh, you are saying
I
body
think
force.
I think it should be body
Uh,
force, but I am not confirmed.
okay. No, no, Jitendra, it will not be a body force. It will be a surface force, and uh, it will be surface force because you see viscous force. Even I mean, leave aside fluid. Let's talk about even solids, which we are more familiar. Like you take your two palms and rub against each other. Okay, uh, there is this friction force, right? I mean, when you try to rub your two palms against each other, there is surface. So, what? Uh, Let me use the word atoms here. What atoms do you think are interacting uh, to generate that force? Do you think the atom that is well within my palm, well within or well inside the palm that is interacting, or it just the atoms that are on the two surfaces are interacting? It is just the atoms which are on the two surfaces which are rubbing against each other, interacting, right? So what I'm trying to say is that the viscous force originates when the fluid particle residing on the surface of this fluid element will rub against the fluid particle of the neighborhood. The fluid particles of the fluid element which are inside the fluid element, though they don't get opportunity to rub against the fluid particles of neighborhood. So viscous force is generated only by those fluid particles of the fluid element which are on the surface, and that's why it is a surface force. It's not a body force. Yes, it is a surface. Does it make sense, Jitendra? Okay. In fact, sigma will take major contribution for from these viscous forces. We will see. Maybe a couple of weeks from now, we will have an expression for how viscosity affects generates forces, and they will be part of this sigma that I have written. Do we have any internal viscous forces in a fluid element? Yes, inside Satvik, inside also there may be viscous forces, but you see what the way we got to these headings, surface and body forces. I said external to the fluid element, right? External to the fluid element. So let me go back here. So this segregation depends on first on what is the system. So see what I said. Forces acting on Fe, forces, external forces acting on Fe. I should write it here also. Later I wrote external, but external forces acting on Fe. So yeah, one fluid particle inside this fluid element itself, one fluid particle is exerting, maybe exerting viscous forces on the other fluid particle. But here, this segregation, what we are making, these definitions, what we are making, are only for those forces which are external to the entire fluid element. So when you consider only forces which are external to the entire fluid element, those forces which are being exerted by one fluid particle on another within our fluid element, that is irrelevant. I am not even paying attention to that. So that these definitions do not apply to those internal forces. Those are internal forces. Have I made sense? Okay. Yes. Yeah. See, this whole idea or the motivation behind this segregation is to draw the FBD of Fe. Okay, so when you draw FBD of Fe, it is clear we need to only consider external forces. So this segregation is only for external forces external to the Fe. I'll wait for 1 more minute and then I'll close this session. All right, I'm closing this session now.